In this quiet stretch of space, scale outruns intuition, while our lives depend on narrow bands of stability. A single wandering asteroid, a solar superstorm, a restless supervolcano, each can bend history in a moment. These risks are not stories from far away. Tunguska and Chelyabinsk were real, and in the deep future the sun will swell. Yet the same cosmic violence forged the elements in our blood, binding our origin to the hazards around us. Because life is fragile, every day and every achievement gains weight. Reason points to a patient response. Become a spacefaring species, spread risk, and stop keeping all of civilization on one world, even if escaping the Milky Way may remain beyond us for a very long time. If this journey speaks to you, please like and subscribe. Let's begin. Modern life rests on a thin set of steady conditions. We need predictable seasons, reliable harvests, clean water, and technology that turns on when we press a button. Global shipping brings food and medicine across oceans. Power grids feed hospitals and data centers. Satellites guide planes and ships and tell farmers when to plant. Behind all of this lies an assumption that the background of nature will not shift too fast. Yet the solar system does not promise calm. It only offers patterns and probabilities. A single large asteroid could strike with little warning and shut down industry in hours. A supervolcanic eruption could dim the sun for years and cut global crop yields to a fraction of normal. A solar superstorm could damage satellites, overload transformers, and push modern life back to a pre-electric rhythm. These are not movie plots. They are events that the Earth has seen before, in different forms and at different scales. Asteroids cross Earth's orbit because gravity moves them along long, stretched paths called ellipses. Most never come close. A few do. Volcanoes build pressure over long periods as magma rises, gases dissolve, and rock cracks. When large systems fail, the blast can spread ash around the world. The sun runs on a magnetic engine that waxes and wanes about every 11 years. During active periods, it can throw out bursts of charged particles and magnetic fields. When these reach Earth, they can disturb our own magnetic shield and drive currents in long wires. Those long wires include power lines. It is hard to hold these risks in mind. They feel far away in time and space. Human brains formed to handle dangers that are close and personal. We are good at reading faces, spotting motion in tall grass, and remembering the path to water. We respond to things we can see and hear and touch. We are much weaker at tracking abstract, low-probability events that unfold over decades or centuries. Psychologists call one trap the availability heuristic. It means we judge the likelihood of a thing by how easily examples come to mind. If an event is in the news, we think it is common. If we have never heard of it, we think it hardly ever happens. This shortcut helps in daily life, but fails with cosmic risk. Many people can recall details of a plane crash, a storm on the evening news, or a dramatic rescue. Fewer can describe the Carrington event of 1859, when the sun sent a storm that lit the sky as far south as the Caribbean and set telegraph lines on fire. Fewer still know the Toba eruption about 74,000 years ago, which spread ash across large regions and likely cooled the climate. The Tunguska blast in 1908 flattened trees across 2,000 square kilometers in Siberia. It was most likely an airburst from a small asteroid or comet. These events sit outside the daily cycle of headlines. They are quiet in memory, even though their lessons are loud. News habits make the gap worse. Media flows toward breaking stories with video and clear villains. Slow, probabilistic threats are harder to frame. An asteroid the size of a house slips by Earth all the time, but only a tiny fraction hit, and most would burn up in the air. That is not a clear story. Solar cycles rise and fall on an 11-year rhythm. Warning signs live in magnetic measurements, not in a single striking clip. Large volcanoes give off subtle gas and heat signals years in advance. That calls for graphs, not a short segment. Schools add to the gap when they skip the basics of how these systems work. Many graduates have never studied asteroid orbits, the sun's magnetic cycle, how Earth's field drifts and sometimes reverses, or the rock layers that record past mass extinctions. A few simple ideas go a long way. Orbital mechanics is the study of how gravity shapes motion. It shows why small pushes over time can change an asteroid's path, and why early detection matters more than last-minute force. Solar activity follows cycles, driven by tangled magnetic fields on the sun's surface. More sunspots often mean more chance of strong storms. Earth's magnetic field comes from moving metal in our planet's core. It shifts and sometimes flips polarity over thousands of years. Rock layers, ice cores, and fossil records give timelines for past impacts, eruptions, and climate swings. None of this is beyond reach. It is a set of tools for seeing our place in a restless system. Seeing the risk is only half the picture. The other half is the record of survival. For billions of years, Earth has stayed within ranges that allow liquid water, stable chemistry, and complex life. This happened while asteroids fell, volcanoes erupted, and the sun slowly brightened over geologic time. Life has been cut back more than once. At least 5 mass extinctions removed a large share of species. Yet, life returned and diversified. The general pattern is harsh and hopeful at once. Shocks arrive, ecosystems collapse, survivors adapt, and new forms spread into open niches. That does not make any single loss small. It does show that the rules of physics and chemistry can support long arcs of complexity, even in a busy, violent system. We are part of that arc. The atoms in our bodies were set up in stars. Hydrogen formed early in the universe. Heavier elements, like carbon, nitrogen, oxygen, calcium, and iron, came later inside stars through nuclear fusion. When massive stars ran out of fuel, they exploded as supernovae and scattered those elements into space. Later, clouds of gas and dust, seeded with this material, formed new stars and planets. Our sun is one of those later stars. Earth formed from the mix and held on to water and air. Given time, chemistry on Earth built self-copying molecules, then cells, then the long chain of life that led to multicellular organisms, brains, language, and tools. The same processes that can harm us also make beauty. The rings of Saturn are shaped by gravity, ice, and the pull of small moons. Auroras appear when solar particles flow along Earth's magnetic field and light up gases high in the atmosphere. Snowflakes grow their crystal forms as water vapor freezes and follows simple rules again and again. None of this cancels the danger. It shows that order and risk share one stage. The sun warms and sometimes storms. Volcanoes build land and sometimes break it. Ice protects and sometimes advances. Impact craters open rock and sometimes end eras. A clear view of risk suggests clear actions. We can reduce impact risk by finding and tracking near-Earth objects. That means sky surveys that scan wide areas every few nights, radar follow-ups that refine orbits, and computers that project paths many years ahead. If we find a rock on a future collision course, small pushes early work best. One method is a kinetic impactor, a spacecraft that rams the asteroid to change its speed by a tiny amount. Over years, that tiny change adds up to a large miss. Another method under study is gravity towing, where a spacecraft hovers near the object and uses its own gravity to tug it slowly. For small objects caught late, civil defense plans can save lives. Evacuations, shelter guidance, and realistic damage maps. For volcanoes, long-term monitoring helps. Satellites track ground motion and heat. Sensors measure gases like sulfur dioxide. Seismic networks listen for deep tremors. With good data, agencies can raise alert levels, close air routes, and protect water supplies. For solar storms, the core tools are space weather forecasts and resilient grids. Spacecraft placed upstream from Earth can detect strong solar wind hours in advance. Grid operators can reduce loads, reconfigure lines, and protect transformers with hardware that blocks unwanted currents. Hardening satellites and keeping backup systems on the ground lowers risk further. Even when we prepare on Earth, a basic vulnerability remains. All of our resources, culture, and memory sit on one planet under one star. Redundancy is a simple idea. Do not keep everything in one place. In space terms, that means becoming a true spacefaring species. The goal is not to abandon Earth. It is to spread risk and keep knowledge alive after worst-case events. Early steps are practical and within reach. Permanent crews in low Earth orbit and cislunar space, depots that store fuel made from lunar ice, and habitats that rotate to provide artificial gravity. Engineers call these large rotating stations O'Neill habitats. They could sit at gravitational balance points, known as Lagrange points, where fuel use stays low. Mars is a harder step, but useful as a long-term second home. It has water in the form of ice, carbon dioxide in the air for making fuel, and gravity that is weak but not zero. Building a self-sustaining base would take decades of steady work. Underground shelters for radiation protection, greenhouses for food, closed-loop water and air systems, and factories that use local rock and soil to make bricks, metals, and glass. The same skills would support mining of small near-Earth asteroids for metals and water. Water is key because it supports life and can be split into hydrogen and oxygen for rocket fuel. These projects feed back to life on Earth. Surveying asteroids teaches us what they are made of. That knowledge can improve mining methods and materials science. Producing power in space and beaming it down by microwave or laser could someday supply clean energy without smoke or waste heat in cities. Moving heavy, dirty industry off-planet would cut pollution and leave more of Earth for living systems. Studying other worlds gives us mirrors for our own. Venus shows what happens when a thick atmosphere traps heat. Mars shows how a once wetter world can dry and cool. Titan, Europa, and Enceladus show chemistry under cold skies and ice-covered oceans. Each comparison sharpens our models of climate, weather, and habitability. Education is the quiet foundation of all of this. When students learn the basics of orbits, energy, and geology, they gain the tools to reason about risk and preparation. Simple classroom labs and clear graphics Make ideas tangible. Swing a weight on a string to feel centripetal force. Use a magnet and wire to see how changing fields induce current. Stack layers of different sands to mimic rock strata. Public drills and honest risk communication build trust. People accept trade-offs when they understand why plans exist and what those plans can and cannot do. Funding and policy matter too. Data must be shared across borders because asteroids and solar storms do not respect lines on a map. Early discovery demands telescopes in both hemispheres and in space, with software that flags small moving dots against thousands of stars. Power grids benefit when regions coordinate and invest ahead of time in transformers that can survive geomagnetic disturbances. Volcano networks work best when scientists, local leaders, and communities stay in touch year after year, not only when the ground shakes. None of this makes us invulnerable. It moves us from fragile by default to resilient by design. It swaps blind risk for measured risk. It turns rare, high-impact events from total surprises into challenges with plans attached. Progress may feel slow because success is quiet. A rock we deflect does not make a headline. A storm that fails to break the grid looks like a normal day. A volcano watched for years and handled with evacuations can feel like a false alarm to those far away. Quiet wins are still wins. The farther view is steady and practical. The solar system is not out to get us. It is a set of physical systems that follow rules. Asteroids move along tracks we can measure. The sun's magnetic surface alternates between tangled and tidy. Earth's interior breathes heat and builds mountains. Over very long times, the sun will brighten and the inner solar system will change. Over shorter times, we can prepare, adapt, and spread out. The tools we build for defense and exploration, better sensors, smarter software, closed-loop life support, radiation shielding, high-efficiency propulsion, have direct, daily uses on Earth. They make hospitals more reliable, farms more precise, buildings more efficient, and disaster response faster. What ties all of this together is a simple stance. Treat the world as it is, not as we wish it to be. Learn the patterns, watch the signals, build margin, share knowledge, practice often, keep backups. Move some of what we care about into more than one place. The same habits that keep a family safe: smoke alarms, insurance, spare batteries. Scale up to a planet and then to a civilization. Space adds new rooms to the house. Global risk work relies on signals we can measure and methods we can repeat. Sky surveys list near-Earth asteroids. Radar and light curves help estimate size, shape, and spin. Computer models project impact chances. Space weather satellites near the Sun-Earth point, L1, a balance spot in space, give minutes to hours of warning. Grid procedures cut harmful currents. Design rules harden satellites, airplanes, and long pipelines. Volcano networks track gas, ground swelling, and tremors. Alert levels link to ready steps for air traffic, water systems, and evacuations. Education materials focus on orbits, the sun's magnetic cycles, and rock layers that record time. Stratigraphy, using simple labs and clear graphics. Public drills keep guidance familiar. Funding plans support open data, cross-border alerts, and shared spare parts for large transformers and communications equipment. To see why these basics matter, look up, step outside on a clear evening, and the bright points have simple names, but the worlds behind them are not simple at all. Venus looks steady near sunset, yet thick clouds and crushing air blanket a surface hot enough to melt soft metals. Those clouds carry droplets of sulfuric acid the same chemical used in car batteries, and near the ground, the air is so hot and dry that most droplets break apart before falling. Mars glows rusty because iron-rich dust covers much of its land. Through binoculars, it's a small disk. Beneath that calm look lies a record of impacts and deep fractures. The moon hangs nearby, white and quiet, but its origin traces to a giant collision that hurled rock into orbit. The debris gathered and became our moon. Jupiter is a bright point to the eye and a banded world in photos. Its strong gravity has reshaped the paths of many comets and asteroids, some redirected, some absorbed, and it drives storms larger than Earth, with winds that circle for years. The scene is beautiful and busy at the same time. Venus hides a slow-moving surface under a lid of clouds. Mars shows its scars in the open. The moon sets a steady rhythm in the rise and fall of tides and helps stabilize Earth's tilt. Jupiter's pull matters across the system, bending the traffic of small bodies that wander near the inner planets. Each object tells part of one story. Gravity and energy shape matter into worlds, and those worlds change through impacts, heat, and radiation. The sky overhead is not a still picture. It is a working system with many moving parts. Take Mars as a focused case. Two small moons, Phobos and Deimos, circle the planet. They look like lumpy rocks rather than smooth spheres, and are likely captured asteroids pulled in long ago from the main belt. Phobos, the larger one, orbits so close to Mars that it rises in the west and sets in the east because it moves faster than Mars spins. Tidal forces, stretches caused by different pull on the near and far sides, are slowly draining orbital energy from Phobos and drawing it inward. Long grooves on its surface likely trace that stress. In tens of millions of years, Phobos will break into pieces or drop into Mars. If it breaks, the rubble could form a thin ring for a while before drifting down. Mars itself keeps records of larger blows. The northern lowlands belong to a feature called the Borealis Basin, which covers a large fraction of the planet's north. A leading idea is that a huge impact early in Mars's life carved out this basin. The object may have been as big as a dwarf planet. Energy from such a hit melts and even vaporizes rock, heats the air, and can strip parts of the atmosphere into space. It can disturb a planet's internal dynamo, the flow of molten metal that powers a magnetic field, so the shield weakens or stops. Without a strong magnetic field, charged particles from the sun can more easily knock gas molecules off the top of the atmosphere over long spans. Spacecraft like MAVEN have measured present-day loss, a slow effect that adds up over millions of years. Another sign of deep stress is Valles Marineris, a canyon system more than 4,000 kilometers long and up to 7 kilometers deep. It is not a river cut. It is a chain of wide troughs and cliffs across a continent's width. Many scientists think the crust stretched and cracked as the nearby Tharsis volcanoes rose and loaded the surface. Shockwaves and heat from early impacts may have helped weaken broad zones of rock, so later forces could pull them apart. After the first breaks, landslides and gradual erosion widened and shaped the walls. The scale points to rapid, powerful change at key times, followed by slower reshaping. Now shift to our star. The Sun is a sphere of hot plasma powered by nuclear fusion in its core. On and above its surface, magnetic fields twist, tangle, and reconnect. When they snap into a new shape, they release flares, sudden bursts of light and particles. Coronal mass ejections, or CMEs, are related events where a bubble of solar material and magnetic field lifts away and speeds outward. If a CME travels toward Earth, it can arrive in 1 to 3 days. When it gets here, it can disturb Earth's magnetic field and drive currents in long conductors like power lines. In 1859, a strong solar storm known as the Carrington event made telegraph systems spark and fail. People saw auroras far from the poles. If a storm of that strength happened now, the effects would reach satellites, GPS timing, radio links, and electrical grids. Power grids can be damaged when extra currents, heat transformers. Satellites can be pushed by changes in the thin upper atmosphere and may drift out of planned orbits. These are engineering problems with known steps to reduce risk, but the link becomes clear when we connect daily tools to the space environment that surrounds them. CMEs also matter over long spans. Charged particles and magnetic fields can strip gas from the top of an atmosphere, especially if a planet lacks a strong magnetic field. Mars likely lost much of its early air this way and is now cold and dry at the surface. Earth is different because our magnetic field, generated by the liquid outer core, guides many particles around the planet or into the polar regions. The field is not fixed. Its strength and direction change slowly, and the poles have reversed many times over geologic history. During parts of a reversal, the field weakens, which lets more particles reach near Earth's space. Ozone can be affected by high-energy particles. Systems in space and the upper atmosphere feel the change most. Life at the surface is buffered by air, water, and soil. Scientists watch the field with ground sensors and satellites because it is part of our shield. Jupiter's role is double. Its gravity has likely reduced the number of long-period comets that cross Earth's orbit by changing their paths or absorbing them. It can also send objects inward from the outer solar system, feeding the inner regions with new bodies. The same gravity that protects can also stir. Jupiter's weather shows how energy moves in a deep, fast atmosphere. Bands of winds blow in opposite directions at different latitudes. Storms start where bands meet. The Great Red Spot is a giant storm that has lasted for centuries, with winds that would overwhelm any structure built on Earth. Lightning flashes above cloud decks. These features do not threaten Earth directly. They show what gravity and heat can do when there is a lot of gas and time to work. The moon's steady pull is the most familiar sign that gravity shapes daily life. Tides raise and lower sea levels and drive currents in bays and estuaries. The leading idea for the moon's origin is the giant impact hypothesis. A Mars-sized body hit the young Earth, ejecting debris that later gathered into the moon. A large moon helps stabilize Earth's tilt over long timescales, which helps keep seasons within ranges that ecosystems can handle. The tides also slow Earth's rotation very gradually and push the moon slowly away from us. Laser reflectors left on the lunar surface let us measure that drift centimeters per year across decades. Venus offers a mirror for climate. It is similar in size to Earth, but its thick carbon dioxide atmosphere and bright cloud cover trap heat by the greenhouse effect. Surface pressure is more than 90 times Earth's. Lead would melt on the ground. Radar mapping lets us see through the clouds and study plains, highlands, and relatively few craters, which suggests parts of the surface were resurfaced in the past. Studying why Venus and Earth diverged helps test models of how atmospheres evolve and how planets hold or lose balance between heat inputs and heat loss. When we connect these examples, a few basic ideas keep returning. Energy flows through systems. Gravity organizes motion. Materials respond by melting, breaking, flowing, or lifting away. Hazards we care about on Earth, impacts, large eruptions, and solar storms are moments when energy delivery is fast and intense. They leave sharp signatures, craters and shocked minerals in rock, ash layers in ice cores, sudden swings in magnetometers. We can read those signs to estimate how often events happen and how strong they can be. Those estimates help set priorities for monitoring and engineering. Watching starts with surveys. Telescopes scan wide patches of sky every few nights to find near-Earth objects. Infrared instruments help spot dark bodies that reflect little sunlight. Radar, when targets pass close enough, measures distance and speed precisely. Light curves the changes in brightness as an object rotates, show shape and spin. These data feed orbit models that project paths for years. If a path crosses Earth's future location, small nudges early work best. The DART mission showed that a kinetic impactor can change an asteroid's motion by a tiny amount. Over time, that small change adds up to a large miss. Volcano monitoring uses a similar mix of signals. Gas sensors near vents and on aircraft track sulfur dioxide and other markers of rising magma. Satellites watch the ground with radar to see swelling or sinking of a volcano's flanks. Seismometers map small quakes that cluster as magma moves. When these data line up, agencies raise alert levels and work through pre-planned steps. Adjust air routes to avoid ash, protect reservoirs, and prepare evacuations. After an eruption, ash removal, water testing, and air quality guidance help cities recover. Space weather forecasting blends solar images, magnetic maps, and upstream measurements from spacecraft. Alerts give grids and satellites lead time to take protective steps. Design standards add hardware that blocks geomagnetically induced currents and improves grounding. Long pipelines and long undersea cables account for space weather in their protection plans. Polar aviation keeps alternate routes trained and ready. Checklists turn rare events into practice tasks. Earth's magnetic field adds a slow rhythm in the background. Ground observatories record direction and strength. Satellites map the field above the air. Rock samples preserve ancient field directions, giving a deep time record of past changes and reversals. A full reversal takes thousands of years, not days, and the fossil record shows life has passed through many of them. Still, during weak phases, extra radiation reaches space near Earth, which is why satellite shielding, better storm forecasts, and robust backups for communication and navigation are practical safeguards. Daily life already leans on this web. GPS timing depends on models of the ionosphere, the charged layer that responds to solar storms. Airlines use space weather bulletins. Farmers and planners use climate records that include signals from volcanoes and solar cycles. Builders and emergency managers use hazard maps that include old flood lines and old ash lines. Science classes use images from Mars rovers and lunar orbiters to teach erosion, landslides, and crater counting. The line between space and home is not a wall, it is a gradient of effects. Mars, with its small moons and wide scars, remains a focus for robots and later, people. Landers and rovers map rocks and test the chemistry of ancient lake beds and river deltas. Orbiters track dust storms that can grow and circle the planet for weeks. Future stations may listen for quakes to map the interior and watch as seasons move carbon dioxide between air and polar caps. Phobos will keep circling lower. Deimos will keep circling higher. Measurements will keep adding up. The sun will keep its cycle. Sunspot counts rise and fall over about 11 years, and with them the odds of strong storms. Agencies that watch the sun post alerts based on what multiple spacecraft see. Engineers fold those alerts into operations. Some storms pass with little effect because systems had margin and operators took steps. Some reveal gaps that guide the next upgrades. Each cycle is another round of testing under real conditions. Jupiter's storms will come and go, and now and then telescopes will catch brief flashes when small bodies hit its clouds. The moon will rise and set, and its distance will increase by centimeters per year. Venus will shine near sunset or sunrise, bright against the dark. Mars will sometimes be close and sometimes far, depending on where Earth and Mars are in their orbits. These motions are regular enough to support plans that stretch across years. Tools built to watch risks also pay off elsewhere. Detectors sensitive enough to spot dim asteroids help in medical imaging and in checking materials for flaws. Software that tracks many moving points against a noisy background helps with traffic, shipping, and wildlife counts. Power electronics made to ride through geomagnetic storms increase grid efficiency in quiet weather. Methods for closed-loop water and air in space habitats feed into clean systems for cities and remote towns. The flow of ideas runs both ways, linking space tools with daily needs on the ground. Operational cadence continues without drama. Survey telescopes in both hemispheres scan on set schedules, and space-based infrared sensors add coverage for dark, cold objects. Spacecraft at the Sun-Earth L1 point provide upstream solar wind speed and magnetic orientation. New plans place monitors near L5 for side view warnings. Power grids link alerts to fixed thresholds for load shedding and transformer protection. Satellite operators map alerts to mode changes and safe hold rules, and aviation advisories cover radio, navigation, and crew dose. Volcano networks align gas release, ground deformation, and seismicity to clear alert levels that map to actions. Mars missions keep collecting weather, dust, and radiation data across full seasons, while orbiters repeat passes to track change through time. Its purpose becomes clear on the next world inward, Venus. Venus sits next door and shows what long, steady stress from a star can do when a planet's defenses fail. The surface stays hot enough to melt lead, and the air presses with about 90 times Earth's surface pressure. Thick clouds ride above a deep haze, and much of that haze holds droplets of sulfuric acid. Several lines of evidence suggest that early Venus may have had shallow oceans and a milder climate, closer to early Earth than to what we see today. Over long periods, the sun brightened, and giant volcanic provinces vented carbon dioxide and water vapor. Greenhouse heating rose. More water evaporated. Water vapor, also a greenhouse gas, added still more heat. As water molecules rose high in the atmosphere, sunlight broke them apart. Light hydrogen escaped to space, while heavier oxygen reacted with surface rocks. The process fed on itself. With no strong global magnetic field to deflect the solar wind, the top of the atmosphere kept losing hydrogen. The result is a stable, hot state. A dense carbon dioxide atmosphere, clouds rich in sulfuric acid, and a ground so hot that most metals would soften. Venus is not violent because of sudden blows. It is violent because steady inputs pushed feedback loops in one direction for a very long time. Mercury offers a different kind of stress test. It is the smallest planet and the closest to the Sunday. With almost no atmosphere to spread or trap heat, temperatures swing hard, near 427 degrees Celsius during the long day, and down around 173 degrees Celsius during the equally long night. Mercury rotates 3 times for every 2 trips around the Sun, a 3-to-2 spin-orbit resonance that locks in because of the planet's shape and tidal forces. Its path is a stretched ellipse, so the Sun's apparent motion does strange things. From some places on the surface, the Sun climbs, slows, drifts backward for a while, then resumes forward motion. Rock expands in heat and shrinks in cold. Over billions of years, that slow breathing helped create long cliff systems called lobate scarps, huge wrinkles where the crust thrust over itself as the planet's interior cooled and the whole body shrank. The landscape records thermal stress, tidal stress, and long cycles that would challenge any power system or lander design. A machine on Mercury must ride out weeks of light, weeks of darkness, and an intense rain of radiation from the Sunday. Warning time matters as much as event size. Some hazards unfold slowly and give decades to act. Others arrive quickly. The impactor that formed the Chicxulub crater at the end of the age of dinosaurs came in at tens of kilometers per second, with no warning for the living systems of that time. There were no telescopes, no sky surveys, no models. The energy release lit fires across continents, drove tsunamis across oceans, and filled the sky with dust and sulfates that dimmed sunlight for months. Today we do scan the sky, but our view still has gaps. Ground telescopes are blind to objects coming from the direction of the Sun because they vanish in daylight glare. At dawn and dusk, the air is unsteady and bright, which makes small, dark bodies hard to pick out. That geometry is the core reason we still miss some close approaches. The Chelyabinsk airburst in 2013 showed this limit in human terms. A stony object about 20 meters across entered over Russia without prior detection and exploded high in the atmosphere. The shockwave broke windows across many cities, and more than 1,600 people were injured, mostly by glass. There was no crater. Damage came from the pressure pulse. The trail looked like a slow, bright fireball, and many people walked to windows to watch. Seconds later, the wave hit. Events in this size range happen on human timescales. They are small in astronomical terms, but large compared to our daily safety plans. They also cluster in the dayside blind spot because small objects are faint and fast. Search programs have improved quickly since the early 1,990 seconds. Surveys sweep the sky on set cadences. Follow-up telescopes measure positions, brightness changes, and sometimes radar echoes. Agencies coordinate orbits, models, and public alerts. NASA's Planetary Defense Coordination Office links discovery work with impact probability estimates and civil protection planning. Even so, the count is not complete. Most of the very large near-Earth asteroids are found, but less than half of the objects larger than about 140 meters, the class that can cause regional damage, are catalogued, and only a small fraction of the tens of meters class is tracked. The planned Near-Earth Object Surveyor, an infrared space telescope designed to see warm, dark bodies against cold space, is intended to close the dayside gap by watching from space. It will still take years of steady work to build a more complete map. Asteroids from the main belt are only part of the picture. Long-period comets arrive from the Oort cloud, a distant, roughly spherical population of icy bodies that likely stretches to tens of thousands of astronomical units. Their orbits are so large that a single circuit can take millions of years. The paths of a few are nudged by passing stars or by the slow pull of dense gas clouds that the solar system encounters as it moves around the galaxy. When a long-period comet is found, warning time can be short months rather than years. because the object spends most of its life far away and becomes bright only when near the sunday. Comets move faster than most asteroids near Earth, often tens of kilometers per second faster, which increases impact energy. A famous example, Hale-Bopp in 1997, was more than 60 kilometers across. It was not headed for us. But if a comet of that size were on a collision course, present methods would not be able to deflect it with such short notice. Comet physics adds uncertainty because jets of gas and dust act like small thrusters and bend the path in ways that change as the surface warms. Comets bring extra challenges beyond speed. As they heat, they shed material in irregular bursts. The jets push in different directions at different times, so trajectory estimates must be updated often, even when impact chances are low. Bright comets can affect Earth indirectly. Dust that peels off along their paths can seed later meteor showers when Earth crosses those streams. These showers are usually harmless, but they remind us that debris from distant sources threads through near-Earth space. The main defense is early discovery and frequent tracking from both hemispheres to increase coverage. A separate, low-probability concern lives at the edge of observation: free-floating, or rogue, planets. These are worlds that formed around stars and were later ejected, or small, cold objects that never built enough mass to ignite fusion. They do not shine by themselves, and far from any star they reflect almost no light. The main way to find them is by gravitational microlensing, where a foreground object's gravity briefly brightens the light of a background star. Surveys have seen short events that suggest Jupiter-mass bodies with no obvious host star. Counts from those surveys are still rough, but they allow estimates of how common such wanderers might be. Over very long times, a massive intruder passing through the outer solar system could disturb the orbits of comets in the Oort cloud, or tweak the paths of distant small bodies. The chance in any given century is tiny. The effect on planning is to define an outer boundary for scenario studies rather than a near-term action item. Venus and Mercury set the near-Sun benchmarks. Venus, lacking a global magnetic field and driven by strong outgassing, shows how a greenhouse can run away until the surface becomes unlivable. Mercury, small and airless, shows extreme thermal swings, crustal shrinkage, and a sky where day and year do not match Earth's simple rhythm. Both help test climate and geology models. Radar mapping of Venus reveals lava plains, high-standing regions, and features that resemble volcanic domes and collapsed calderas. Tracking heat and gas from orbit can test whether the planet still vents from deep within. On Mercury, high-resolution images show scarps that cut across craters, which means the cliffs formed after many impacts and are part of the long cooling of the interior. Detection and warning for impact hazards hinge on geometry and wavelength. Ground telescopes do well at night against a dark sky, but cannot see through daylight glare. Space-based infrared telescopes can look outward from inside Earth's orbit, or from a trailing orbit, and see the warm glow of near-Earth objects, regardless of how dark they appear in visible light. Once an object is found, follow-up observations refine size, reflectivity, rotation, and whether it travels alone or with a small companion. A bright, reflective stony asteroid and a dark, carbon-rich asteroid of the same size reflect different amounts of light. Thermal measurements help tell them apart. That matters because mass and structure affect how a deflection push will work. Civil measures fill gaps when warning is short. Simple practice steps reduce harm from small impacts. Stay away from windows after a bright sky flash. Move indoors and wait for the pressure wave. For medium-sized objects with days of lead time, emergency planners can estimate the entry path and the footprint of likely damage and adjust evacuations much like they do for hurricanes and wildfires. Clear maps and short messages help. For the rare, very large class of impactors, long-term readiness means testing deflection methods, building international decision paths, and keeping launch capabilities that can reach targets on set timelines. Kinetic impactors, spacecraft that strike a body to change its speed slightly, are the simplest tool. Over years, a tiny change becomes a big miss. For very large bodies and short notice, current methods are not enough, which is why survey completeness matters. Solar activity interacts with these plans. The same star that drives climate and weather also shapes the space environment, where our satellites, power grids, and radio systems operate. Space weather monitors sit near the Sun-Earth L1 point to sample the solar wind and magnetic field before it reaches Earth. When a coronal mass ejection is on the way, the orientation of its magnetic field matters. If it points south relative to Earth's field, coupling is stronger and disturbances grow. Alerts allow grid operators to reduce loads, change configurations, and delay maintenance. Satellite controllers can switch to safe modes and limit maneuvers. Polar aviation can adjust routes to avoid radio blackouts and reduce radiation exposure. Design standards add hardware that blocks geomagnetically induced currents and improves grounding for long lines and pipelines. Long-term solar forcing also shapes atmospheres. Venus's ongoing loss of hydrogen at high altitudes is a marker of its early water history and continued escape. Earth retains its water in part because our magnetic field deflects much of the solar wind, and because gravity holds heavier molecules near the ground, the field itself changes over time. Rock records show many reversals, when magnetic north and south swapped places. During parts of a reversal, the field weakens, letting more energetic particles reach near-Earth space. Most life on the surface is shielded by air, water, and soil, but satellites, high-altitude aircraft, and power systems feel the difference. That is why magnetic field monitoring, space weather forecasting, and robust backups for communication and navigation are part of routine planning rather than special projects. Mercury's orbit and crust show how thermal and tidal stress write long records in rock. Venus's thick air and bright clouds show how small shifts in energy balance can have large effects when feedback loops activate. The Oort cloud and long-period comets show that our neighborhood stretches far beyond the planets we can see with the eye. Rogue planet studies show that some risks are so rare and broad that they set the bounding cases for models instead of driving yearly budgets. In each case, the inputs to planning are the same: measure carefully, share data, and refresh models as new evidence arrives. Practical projects move in parallel. Survey telescopes scan the sky on regular schedules and pass candidates to radar and photometry teams. Data centers publish orbit solutions and impact probabilities that update with each new arc of observation. Space-based infrared instruments add coverage for dayside approaches. Mission teams test deflection physics on small, safe targets to validate equations that guide future work. Power grid operators map transformer risks from geomagnetically induced currents and stock critical spares. Space weather services tie satellite alerts, polar aviation guidance, and pipeline procedures to clear thresholds, so actions are automatic when values cross set lines. Operational details carry weight. A dayside asteroid is found earlier if the survey platform looks outward from an orbit closer to the Sun than Earth. A small comet's path is pinned down faster if telescopes in both hemispheres coordinate to cover more hours of each day. A local safety message after a bright sky trail needs to arrive before the pressure wave, which means automatic triggers and scripts ready for broadcast. A grid operator needs thresholds linked to transformer models, not just general warnings. A satellite needs safe mode rules and fault trees that align with alert codes. Practice makes the steps smooth. Venus, Mercury, near-Earth asteroids, distant comets, and the rare possibility of rogue planets together outline how different parts of the solar system can produce stress. Some pressures are constant, like sunlight and the solar wind. Some arrive in bursts, like impacts and geomagnetic storms. Some unfold over long spans, like atmospheric loss and crustal cooling. The mix changes from place to place. Planning follows the mix. Watch what moves fast, model what moves slowly, and keep systems ready to act when signals cross set points. That checklist also has to reach past the sun's boundary, where visitors can appear without warning. Interstellar visitors show that the space between stars is not empty. In 2017, telescopes noticed Oumuamua only after it had swung past the sun and was speeding away on a path that would never return. The changing brightness suggested a long, thin body or a flat shard tumbling. Either way, it was too fast for any probe we had to catch. In 2019, Comet 2I, Borisov, arrived with a little more warning. It looked like an ordinary comet but moved on a hyperbolic track that did not close around the Sunday. Both cases exposed gaps. Objects coming from the sun's direction hiding glare. Very dark bodies stay faint until close. Interstellar visitors brighten only near perihelion, giving short windows for study. The set of possibilities also includes artificial structures, like thin sails or fragments from other civilizations. None has been confirmed, but the practical point stands. Our early warning net for interstellar objects is incomplete. Activity below our feet is constant as well. Earth's magnetic field, our shield against many charged particles, is powered by a dynamo in the liquid outer core. The field wanders, strengthens, weakens, and has flipped polarity many times. A reversal is not a switch you throw. It unfolds over hundreds to thousands of years. During weak phases, overall strength can drop to a small fraction of normal, allowing more energetic particles into near-Earth space and the upper atmosphere. Ozone chemistry can be disturbed. Satellites and high-altitude operations see higher radiation dose and more glitches. Life at the surface is buffered by the atmosphere and oceans, but technology feels the change directly. Rocks record the last full reversal about 780,000 years ago. Timing between reversals varies widely, so overdue is not a clock. The sensible frame is steady monitoring and design margin in systems that work in space and near space. Plate tectonics runs on stress and release. Earth's shell is divided into moving plates. Boundaries stick, load, and slip. A few centimeters of motion per year can store vast energy over decades. Failure happens in seconds to minutes. The 2004 Indian Ocean earthquake shifted enough mass to shorten the day by a few microseconds and launched a basin-wide tsunami. Subduction zones host the largest events. Strikes slip faults slice long valleys. Normal faults open basins where crust thins. Preparedness scales from building codes and retrofits to early warning that buys seconds enough to shut valves, slow trains, and drop operating rooms into safe modes. Volcanoes mark the other half of the slow engine. Many eruptions are small to moderate, yet they can push sulfur into the stratosphere and dim sunlight for a year or two. Tambora in 1815 did that, and 1816 became the year without a summer across parts of the northern hemisphere. Supervolcano is a size label. Eruptions ejecting more than about 1,000 cubic kilometers of material. Yellowstone has produced large eruptions in the past, plus many smaller events like lava flows and hydrothermal blasts. Recurrence intervals are statistics, not schedules. Planning focuses on ash fall, aviation impacts, water systems, and short-term cooling. Ash is heavy and abrasive, clogs engines, scratches lungs, and collapses roofs when wet. Even eruptions well below the superthreshold can spread ash across states and stress food systems if harvests fail. None of this calls for guesswork. Caldera systems are watched with GPS and radar to see ground rise and fall. Gas sensors measure sulfur dioxide and other markers of rising magma. Seismic arrays map swarms that indicate new pathways. The goal is not to predict a day, but to map alert levels to set actions. Reroute flights when ash reaches cruising heights. Shift water intakes when rivers turn to slurry. Advise on masks and indoor air. And prepare shelters from ash for vulnerable groups. The same measure, decide, act pattern that guides storm response applies here with different inputs. Back in space, warning for interstellar bodies is a matter of geometry, wavelength, and cadence. Wide-field telescopes scan the sky every few nights to catch fast, faint movers. Space-based infrared sensors see warm objects against cold backgrounds and are less bothered by glare. Software links point detections into tracks and flags motion that does not fit bound orbits. Once an object looks interstellar, follow-up must be quick. Photometry for spin clues, spectroscopy for ices and minerals, and radar if distance allows. The window is brief because these bodies pass once and go. Intercept missions would need high delta-V propulsion or a pre-staged ready probe parked where launch windows are wide. Engineers study solar sails, electric propulsion, and gravitational assists to raise practical reach. Comets from the Oort cloud raise similar issues. They can give only months of warning between discovery and perihelion. Speeds are high, and jets of gas act like random thrusters that change the path as the surface warms. Early detection from multiple latitudes, continuous tracking, and fast sharing of updated trajectories are the core defenses. For large, fast bodies with short notice, deflection is not realistic. Civil protection shifts to impact prediction, evacuation maps, and infrastructure safety. Magnetic field changes form the background for space-based systems. The South Atlantic anomaly, a region of weaker field, already raises radiation dose for satellites that cross it. Operators respond with hardened electronics, error-correcting memory, and planned instrument shutoffs. If global field strength drifts lower over centuries, such zones could widen, which makes these practices more important for low Earth orbit fleets. Navigation that uses magnetic headings depends on local declination updates. Aviation and marine guidance blend magnetics with gyros and satellite navigation to avoid single-point failure. Tectonics and volcanism connect to climate and food security. Eruptions that reach the stratosphere scatter sunlight and can cool the surface by fractions of a degree for a season or two. Monsoons shift, yields change. Risk managers read volcanic aerosol layers in ice cores and link them to past harvests to shape reserves and trade plans. Bridges, dams, ports, and pipelines are designed with shaking intensities and fault maps in mind. Early warning times for quakes are short but valuable. Seconds to tens of seconds are enough to shut down gas lines, open fire station doors, and pause surgery. Generation ship studies explore closed life for centuries. Teams use Monte Carlo simulations, many randomized runs, to test crew size, genetic health, maintenance, and social stability under different rules. Even with optimistic assumptions, diversity declines unless the starting population is large and carefully managed. A common minimum for long-term genetic health sits in the range of 5 to 10,000 people. That number drives mass and volume far beyond current launch capability. Every person needs air, water, food, light, and space. Every person produces waste that must be recycled. Every person adds to heat, load, and system wear. All closed loops leak and drift. Buffers and maintenance buy time, but errors and disease add noise. Over centuries, noise accumulates unless countered by fresh inputs of parts, knowledge, and people. Design implications are clear. Many small linked habitats resist total failure better than one giant one, because problems can be isolated. Diverse food webs, plants, algae, insects, and fish spread biological risk. Libraries of spare parts and detailed repair manuals help counter knowledge loss. Training that rotates crew through multiple roles builds redundancy in skills. Governance models must include clear procedures for conflict and resource rationing. Intergalactic timescales amplify every weakness, but research does not go to waste. Closed-loop water and air, stable agriculture under artificial light, and fault-tolerant control systems feed back into submarines, remote bases, and cities that aim for low waste. Closer to home, practical steps improve detection and response. Telescopes in both hemispheres hand off targets as night sweeps around the planet. Space-based infrared eyes placed off the Earth-Sun line watch the dayside blind spot. Lagrange point monitors at L1 sample solar wind before it reaches Earth. Future sensors near L5 can give side views of solar eruptions that reveal 3D shape and timing. Orbit solutions update with each new set of measurements and are shared under common formats, so agencies and observatories can act without delay. For civil defense, scripts triggered by bright daytime fireballs push short. Direct messages, stay away from windows, move indoors, wait for the pressure wave to phones and radio within seconds. On the geophysics side, magnetometer arrays and satellites record field drift. Iron alloy experiments at high pressure help constrain core behavior. Seafloor cables sense changes in induced currents that map to field motion. Dense GPS networks, INSAR radar, and ocean bottom seismometers track strain along plate boundaries. Where early warning is viable, sirens and smartphone alerts move faster than shaking by a few seconds. Drills teach people to drop, cover, and hold on, to move uphill in tsunami zones, and to keep dust masks and water ready for ash fall. Large calderas remain under steady watch. Ground uplift and subsidence are tracked season by season. Gas ratios shift as deep fluids move. Swarms of small quakes come and go. Most signals reflect normal breathing of a living hydrothermal system. When patterns depart from baseline, alert levels adjust. Action plans connect each level to steps for parks, towns, air routes, and water managers. The same approach applies at Taupo, Toba, Era and Campiflegrae. None of these systems run on a timer. All benefit from quiet, continuous measurement and clear communication. Interstellar objects, magnetic drift, plate motion, volcanoes, and long-duration habitat studies map different slices of one picture. Some pressures are constant, like sunlight and solar wind. Some arrive in bursts, like impacts and geomagnetic storms. Some unfold over centuries, like field changes and crustal cooling. Planning follows the mix. Widen the watch for fast movers, harden systems for radiation and shaking, link alerts to actions, and test closed loops where people and machines must live for long periods without resupply. Galactic motion sets the backdrop for everything closer to home. Our solar system travels around the Milky Way's center at about 230 kilometers per second, completing one circuit in roughly 225 million years, a galactic year. During that long orbit, the sun and planets bob up and down through the galaxy's midplane, where gas, dust, and magnetic fields are denser on average. Crossings expose the heliosphere, the sun's magnetic bubble, to higher cosmic ray flux. Cosmic rays are high-energy particles from outside the solar system. When more of them reach near-Earth space, they can change atmospheric chemistry and add to mutation rates. Several fossil and rock record studies report extinction pulses spaced tens of millions of years apart. The exact timing and cause remain debated, but the pattern is consistent with periodic changes in radiation and impact rates as the solar system moves through different galactic neighborhoods. The journey also brings the sun past giant molecular clouds, cold, dense regions that can span dozens of light years. These clouds can compress the heliosphere, letting more galactic particles in, and their gravity can tug on the outer fringe of the sun's comet reservoir, the Oort cloud. The Oort cloud is a distant shell of icy bodies that extends far beyond the planets. A nudge there can send comets inward on long, stretched paths. Our system is now traveling through the local interstellar cloud, a slightly denser patch of gas and dust. As the heliosphere moves through such regions, its size and shape shift. A smaller bubble means more cosmic radiation in the inner system and more wear on satellites, power systems, and electronics. Over thousands of years, those small changes can add up in climate records and in the genetic hints carried by living things. Close stellar encounters add a different kind of disturbance. Every few million years, another star passes the sun at distances of a few light years. Most passes barely stir the outer comet cloud, but a close one can raise the odds of long-period comets visiting the inner system. Gliese 710, a red dwarf now visible in the constellation Serpens, is on a path that should bring it to within roughly 1 light-year of the Sun in about 1.3 million years. At that range, its gravity will likely jostle the Oort cloud enough to send a comet shower inward that could last for millions of years. Such a shower would not look like a single storm. It would show up as a sustained rise in the number of comet paths crossing the orbits of the planets. Massive stars that end their lives as supernovae pose another large-scale hazard. A supernova is the final explosion of a large star after it runs out of nuclear fuel. If one went off within roughly 50 light-years, the blast of high-energy photons and particles could thin Earth's ozone layer and raise ultraviolet light at the surface for years. Trees, plankton, and many other parts of the food web would feel the stress. Sea and rock samples contain traces of radioactive iron that point to one or more nearby supernovae in the last few million years. So this is a real process rather than a thought experiment. Most candidate stars are far enough away to be safe on human timescales, but risk is not zero. Betelgeuse, a red supergiant in Orion, is one well-known example of a star in a late stage of fusion. It could explode in the next 100,000 years or more. Its exact timetable is uncertain, but the mechanism is understood. Even without outside triggers, the solar system changes from within. The planets tug on one another in ways that are simple in pairs and complicated in groups. Small differences in position and speed grow over time, a hallmark of chaos. Long computer simulations that vary starting conditions show that inner planet orbits wander in phase and shape over tens to hundreds of millions of years. Mercury, being the smallest and closest to the Sun, shows the largest spread in outcomes. General relativity adds an extra twist by advancing Mercury's perihelion, the point of closest approach each orbit. In a small fraction of runs, Mercury's orbit becomes highly elongated and can, over billions of years, either collide with Venus or be ejected. Those rare paths also change the tugs on the other inner planets, which could shift Earth's orbit modestly. A slightly closer or slightly farther path would alter average temperature and ice cover over very long times. The Moon's slow drift adds another layer. Tidal friction moves energy from Earth's rotation into the Moon's orbit, lengthening our day and increasing the Earth-Moon distance by about 3.8 centimeters each year. A large moon helps steady Earth's axial tilt. As the Moon recedes, that stabilizing effect weakens. Models suggest that in far future epochs, Earth's tilt could vary more widely, changing the pattern of seasons and the placement of climate zones. Ocean tides will weaken as distance grows, which changes coastal mixing and the rhythms of some ecosystems. None of this is sudden on human timescales. The key point is that long, slow processes keep running in the background. The Sun itself evolves on its own clock. As it fuses hydrogen into helium, its core contracts slightly and the outer layers brighten. This slow brightening adds energy to Earth's climate system. With enough increase, feedbacks involving water vapor and clouds can push the planet into a moist greenhouse state. Model studies indicate that in roughly 1 billion years, oceans could retreat and then be lost to space over time, leaving hot, dry surface conditions. That timeline arrives long before the Sun's final stages. Later, when core hydrogen is gone, the Sun will grow into a red giant and extend its atmosphere outward by many times. Mercury and Venus will almost certainly be engulfed. Earth may escape physical swallowing depending on mass loss and tides, but even a close pass would strip the atmosphere and sterilize the surface. The outer planets will persist, yet their environments will be altered by the changing light and wind of the swollen star. These drivers, galactic crossings, cloud passages, stellar flybys, nearby supernovae, chaotic orbital drift, lunar recession, and solar evolution act on very different timescales. Some deliver fast pulses, like a comet shower peaking over a few millennia. Some stretch over millions to billions of years, like the Sun's brightening or the Moon's retreat. The effects overlap rather than line up, so the environment at any given time is the sum of many rhythms. Researchers sort these factors by how far they reach and by what can be measured now. Cosmic ray changes tie into chemistry in the upper atmosphere. Comet delivery changes impact rates. Orbital drift nudges long-term climate baselines. Axial tilt swings redraw wind belts, currents, and coastlines over deep time. Tracking this layered picture uses tools from many fields. Astronomy maps the galaxy's structure. measures star motions, and predicts close approaches far in advance. Space probes at the edge of the heliosphere record the transition from solar wind to interstellar space and show how the protective bubble swells and shrinks. Ground detectors log cosmic ray intensity and link spikes to solar events and slower galactic cycles. Laser ranging to retroreflectors on the Moon measures the Earth-Moon distance to the millimeter, setting tight limits on tidal evolution. Paleontology builds credible extinction timelines by combining fossils, ash layers, impact markers, and isotope ratios. Climate models test how extra radiation, or extra dust, would move temperature, rainfall, and ocean circulation. Orbital simulations sample many slightly different starting points to draw maps of likely and unlikely futures. Close star passes, cloud crossings, and supernova candidates are not items we can influence, but their signatures shifted comet statistics, altered cosmic ray spectra, and isotope traces in rocks and ice are observable. Improving sky surveys in visible and infrared light increases the odds of catching long-period comets earlier in their approach. Better catalogues of nearby massive stars refine supernova distance estimates and likely timescales. Long baseline radio and infrared studies of molecular clouds define where dense regions lie along the Sun's path. Each improvement turns a vague story into one with timestamps, directions, and ranges. Inside the solar system, the same discipline applies. Impact rates adjust when comet showers rise, so crater counts on the Moon and Mars help cross-check models. Geomagnetic records track field strength over time, which ties into how well Earth deflects charged particles during weak phases. Glacial deposits and deep-sea cores preserve signals of tilt and orbit cycles, the Milankovitch rhythms that guide ice ages on 100,000-year scales. Those natural cycles sit on top of the much slower drifts, linked to the Moon's recession and to chaotic orbital shifts. In this widened frame, the solar system is part of a larger, changing environment. The Sun's path through the galaxy sets exposure to radiation and encounters. The galaxy sets the supply of passing stars and clouds. Within that setting, the planets exchange tugs, the Moon slowly steps away, and the Sun brightens and ages. The picture uses ordinary physics, gravity, radiation, magnetism, heat. The outcomes depend on amounts and timing: how dense a cloud is, how close a star passes, how strongly Mercury's orbit is perturbed, how fast the Moon recedes, how quickly the Sun's brightness rises. Different clocks, one system of rules, many ways for energy to move through matter over deep time. Periodic claims in the fossil record, peaks every 26 to 30 million years, have been proposed to match midplane crossings. Other studies argue that sampling gaps blur the signal and that impacts, volcanism, and sea level change can overlap to mimic a rhythm. The safe takeaway is modest. Galactic position can modulate background stress, while local geology turns that stress into specific outcomes. The local interstellar cloud itself looks patchy. Estimates suggest the Sun will remain inside portions of it for thousands to tens of thousands of years, then enter regions of different density. Each step changes the heliosphere's size by a little, which is enough to matter to satellites and high-altitude flight. Long-term orbital studies also produce small but important numbers. In many runs, Mercury's path stays bounded, yet a percent-level fraction show large elongations that end in ejection or collision with Venus within about 5 billion years. Such rare branches are not a forecast for a given date. They quantify tails of the distribution. When Mercury's orbit stretches, the pattern of tugs shifts. and Earth's orbital shape can change by a few percent. That is enough to alter the cycle and strength of ice ages over deep time. Mars, which lacks a large moon, illustrates the tilt problem. Its obliquity can swing wildly, rearranging climate belts. Earth's large moon reduces such swings today. As distance grows, the guardrails widen. Supernova thresholds carry similar ranges. A detonation at 10 light-years would be a very different event than one at 50, and the angle of incoming radiation matters because Earth's magnetic field and atmosphere distribute energy unevenly. Even without a direct hit, a nearby blast can leave traces: nitrates in ice, odd isotopes in sediments, and shifts in tree ring chemistry. Gliese 710's flyby, by contrast, is a gravitational event with a long tail. The comet influx it starts could ebb and flow for millions of years after closest approach. Each driver leaves a distinct fingerprint in the physical record, which is how scientists separate overlapping causes in deep time. Recent impact history lives in the record, not just in theory. In June 1908, over remote Siberia, the Tunguska airburst flattened more than 2,000 square kilometers of forest. The blast yield was on the order of tens of megatons, likely from a stony body tens of meters across that broke apart high in the atmosphere. If a similar object had detonated above a dense city, the shockwave and thermal pulse would have produced mass casualties and a belt of structural failure stretching far beyond the epicenter. In February 2013, over Chelyabinsk, a roughly 20-meter object arrived on a shallow path and exploded around 30 kilometers up. The pressure wave broke windows across many towns, and more than 1,600 people were injured, mostly by glass. These cases define the lower edge of a spectrum. Larger objects appear less often, but the energy they carry scales fast with size and velocity. The background truth remains simple. The inner solar system is a place where small bodies cross planetary orbits. Earth will meet more of them. Survey work has improved, yet gaps persist. New finds continue to surprise because geometry and reflectivity work against us. Asteroid 2022 AP7, found in twilight conditions, is over a kilometer wide and moves on a path that crosses Earth's orbit while staying mostly interior to it. Calculations show no impact risk on century scales, but its late discovery highlights how much sky remains hard to cover from the ground, especially near the Sunday. Many potentially hazardous asteroids are dark, rotating, and small enough to evade easy detection until they pass close. A fraction approach from the day side, where glare and daytime turbulence suppress sensitivity. Even with more sensitive detectors, sky coverage and cadence limit what can be seen each night. Practical defense begins with knowing what is out there and what it is made of. Size, composition, and spin state control how an object responds to a push. A loosely bound rubble pile behaves differently from a solid iron body. A fast spinner reacts differently than a slow one. The DART mission offered the first clean test of a kinetic impactor, changing the period of the small moonlet Dimorphos around Didymos by nudging it. The European Space Agency's Hera spacecraft will follow up with close measurements of crater shape, ejector, and internal structure to calibrate momentum transfer models. This sequence measure, test, refine, turns a one-off demonstration into a tool with error bars. At the same time, it underlines the limits. DART had years of planning, a small, well-chosen target, and no time pressure from an incoming threat. A real deflection attempt would add clock pressure, orbital uncertainties, and a target that may be spinning, elongated, or binary. The nuclear option exists on paper and in simulations. Detonations near a surface can vaporize and spoil material, creating a rocket-like push. A subsurface detonation, drilled or placed in a natural cavity, couples energy more efficiently, but demands a rendezvous and operations in a weak gravity environment. Fragmentation is a major risk. Breaking a large body into many smaller pieces can avoid global climate effects, yet still create multiple regional disasters if the fragments stay on impact trajectories. Timing is also tight, too early, and uncertainties in how the blast couples to a rough surface can leave fragments with small but still dangerous impact probabilities. Too late, and even a strong push will not move the path enough. Any serious plan would require precise size and composition data, a delivery system ready to launch on short notice, and international legal frameworks for using nuclear devices beyond Earth. Space-based infrared surveys address the dayside blind spot. Operating above the atmosphere removes glare and weather, and thermal emission reveals warm, dark bodies that reflect little visible light. A dedicated mission can scan near the Sun's direction from an orbit that trails Earth, or from a solar orbiting platform inward of Earth. With a few years of operation, such a system can raise the completeness for objects larger than roughly 140 meters, a size that defines a common threshold for regional damage. Early discovery lengthens the timeline for decisions, turning brute force pushes into small, well-timed nudges. Nevertheless, detection does not equal mitigation. Moving a mountain-scale object by millimeters per second requires large momentum transfer and excellent knowledge of mass and spin. Communication between discovery teams, orbit modelers, mission designers, and civil authorities becomes part of the defense, so formats, thresholds, and playbooks matter as much as telescopes. Impact climate effects depend on where and what hits. An ocean strike generates a train of tsunamis that radiate across basins and push far inland on low coasts. Plumes inject water vapor and salts high into the atmosphere. The short-term radiation budget and chemistry shift. A land strike into sedimentary basins with fossil carbon and sulfur can loft dust and sulfate aerosols into the stratosphere, reflecting sunlight and cooling surface temperatures. Models of Chicxulub-scale impacts, about 10 kilometers across, show years to decades of reduced light, falling temperatures, and disrupted photosynthesis. Food webs then stress from the base upward. Smaller impacts still matter. Sub-kilometer objects can cause regional failures of crops if the dust and aerosols rise high enough. Cooling is not the only path. Fires ignited downwind of thermal pulses add soot that darkens snow and ice, feedbacks that shift melt timing, and smoke layers that alter cloud formation. Planning for these cases draws on volcanic analogues, Tambora in 1815, Krakatoa in 1883, and on ice core records that tie aerosol loadings to temperature anomalies. Teleconnections extend the reach of a single eruption or impact. When the stratosphere loads with sulfuric aerosols, sunlight reflects before it warms the surface. The equator to pole temperature gradient can change, which in turn shifts jet streams and storm tracks. Monsoon strength varies with land-sea contrast. Small shifts in timing can mean much less rain during key weeks. Ocean circulation integrates, changes more slowly. Surface cooling modifies evaporation and density that can propagate through currents on year-to-decade scales. Grain markets and fisheries respond to these signals in real time, which means climate-aware reserves and diversified supply lines are part of resilience. The same models used to forecast seasonal shifts can be adapted with impact-specific aerosol inputs to produce regional guidance for water, energy, and food managers. Solar storms test a different layer of infrastructure. Coronal mass ejections carry magnetic fields and plasma that can couple to Earth's magnetosphere. If the incoming field points south relative to Earth's field, coupling is strong, energy flows into near-Earth space, and currents are induced in long conductors. The March 1989 storm tripped the Hydro-Quebec grid within minutes. That event was not extreme by historical measures. It was a mid-range reminder that long lines and large transformers are vulnerable. A Centennial-class storm could push many grids into blackouts, damage transformers that take months to manufacture, and disrupt GPS timing that underpins finance, telecom, and logistics. Satellites face drag spikes when the upper atmosphere heats and expands. Low Earth orbit fleets would need frequent orbit maintenance to avoid crowding at lower altitudes. High-frequency radio fades. Polar routes divert. Pipelines see corrosion patterns shift with induced currents. Mitigation is concrete. Spacecraft at the Sun.Earth-L1 point provide tens of minutes to an hour or two of lead time by sampling solar wind speed and magnetic orientation. Solar imagers track active regions and halo CMEs that point toward Earth. Forecast centers issue watches and warnings keyed to thresholds that grid and satellite operators have planned against. Hardware fixes include series capacitors and neutral blocking devices that limit geomagnetically induced currents, better grounding practices, and transformer designs tolerant of half-cycle saturation. Procedural fixes include load reduction, postponing maintenance so more lines are available, and entering safe modes on satellites. Aviation advisories cover radio outages and radiation dose at flight levels. Exercises between utilities, satellite operators, and aviation authorities turn warnings into actions without delay. Forecast skill is improving, but bounded by physics. CME launch conditions depend on magnetic structures that can be hard to measure on the far side of the sundae. The 3D shape of an ejection and the orientation of embedded fields evolve as it travels through the solar wind. Multi-point monitoring helps. Spacecraft at L5, 60 degrees behind Earth in its orbit, can watch regions that will rotate toward us and image CMEs from the side to constrain geometry. Data assimilation, blending images, in situ measurements, and magnetograms into models adds lead time and narrows uncertainty bands. For all that, the biggest storms remain low-frequency, high-impact events. Systems must be designed to ride through them, not just forecast them. Superflares on sun-like stars mark the upper bound of solar events. Surveys that stare at many stars at once have recorded bursts far larger than any directly seen on our sundae. Our sun rotates more slowly and has a quieter magnetic cycle than many flare-active stars in those catalogues, which reduces probability, yet the tail risk exists. The practical response is to build standards that do not assume an upper limit close to recent experience. Satellites need safe hold modes that trigger on multiple indicators, not just one. Memory with strong error correction, shielding tuned to likely particle spectra, and graceful degradation pathways that preserve core functions. Grids need spare transformer programs and regional mutual aid agreements. Pipelines, rail, and aviation need procedures that can run for days on backup communications when high-frequency links fail. Budgets and priorities show where society places risk relative to convenience. The Planetary Defense Coordination Office coordinates surveys, impact probability analyses, and response exercises. Its funding is modest when compared to the value at stake. Near-Earth Object Surveyor aims to close a major detection gap, but procurement and launch schedules add years before full catalogs arrive. Even with perfect detection, a working defense demands tested deflection systems, launchers on call, and international decision lines that can move fast. In the space weather arena, the cost of hardening a grid is visible in the next rate case. The cost of not hardening appears only after a blackout. Standards, bodies, insurers, and regulators shape those choices as much as engineers do. Public communication is part of the technical system. Clear, short messages save lives. When a bright daytime trail appears and a pressure wave is seconds behind, step away from windows, move indoors, wait for the boom. Space weather alerts need plain thresholds that map to actions. Reduce load now, shift polar routes, pause critical maneuvers. Volcano and earthquake systems already use color codes and alert levels. Asteroid and space weather messages benefit from the same clarity. Drills make guidance familiar. Post-event reports that explain what worked and what did not keep learning loops tight. Research continues to pull basic facts into applied use. Characterizing asteroid interiors by combining radar, thermal data, and small landers refines mass and porosity estimates that feed deflection models. Laboratory experiments on shocked rocks improve scaling laws for cratering and fragmentation. High-fidelity CME models, constrained by multi-point data, sharpen arrival time and magnetic orientation forecasts. Power system test beds inject synthetic geomagnetically induced currents to validate protective gear. Long ice core records align volcanic aerosol peaks with temperature proxies to bound climate sensitivity to stratospheric sulfate. Each advance narrows uncertainty, which in turn trims the cost of over- or underbuilding defenses. International coordination matters because hazards do not stop at borders. Survey telescopes in both hemispheres hand off targets as night moves around the globe. Data centers publish orbit solutions and update probabilities as new arcs arrive. Space weather data flow from multiple agencies to common dashboards used by utilities and airlines worldwide. Volcano ash advisories route flights across oceans. Agreements on sharing spare transformers and satellite ground station capacity reduce restoration time after a large event. Exercises that span agencies and countries make it more likely that warnings become synchronized actions when minutes count. None of these steps require new physics. They use measured signals and engineered responses. The practical levers are coverage, cadence, redundancy, and margin. Watch more of the sky more often. Add viewpoints in space. Design systems to fail safely and recover quickly. Keep spares where they are needed, and write procedures that trigger on data, not on debate. Asteroid impacts, volcanic aerosols, and solar storms are different sources that stress the same targets: power, water, food, communication, transport. Cross-training between sectors helps because solutions often rhyme. Isolate faults, shed load, buffer supplies, and restore in steps. The record already shows that small events reveal weaknesses. Fixing those weaknesses ahead of the larger ones is the work at hand. Violence does not only arrive from the sky. A large share of it is built into Earth itself. The crust we stand on rides slow currents of hot rock. Gases move upward along cracks. Water and heat react to change minerals and open new paths. When these flows scale up, the results can be global. The Siberian traps are a stark example. About 252 million years ago, vast sheets of lava poured across what is now northern Asia. Geologists call such regions large igneous provinces, huge fields of basalt laid down over relatively short geologic time. During the Siberian event, eruptions fed through long fissures again and again. Lava spread in layers. Hotter rocks baked coal and organic-rich sediments. Gases vented in great volumes. Carbon dioxide warmed the air. Sulfur dioxide formed sulfuric acid aerosols that reflected sunlight. Methane, released from warmed seafloors, joined the mix. Oceans lost oxygen. Reefs collapsed, and more than 90% of marine species disappeared along with most land species. Rock cores show ash beds stacked with flood basalts, a layered record of repeated pulses that lasted hundreds of thousands of years. The scale dwarfs anything in recorded history. Enough lava to cover areas the size of continents in flows hundreds of meters thick. Large igneous provinces have formed more than once. The Deccan traps in India started before and continued during the time of the Chicxulub impact 66 million years ago. They built thick stacks of lava flows, step by step. The timing is close enough that many researchers study how impact-driven dust, soot, and sulfate aerosols interacted with the gases and particles from the eruptions. Aerosols are tiny droplets or grains that hang in air. Sulfate aerosols reflect sunlight and cool the surface. Soot absorbs sunlight and can warm the air while still dimming ground-level light. The combined effect depends on how high particles rise and how long they stay aloft. Stratigraphic sections in India and around the world show chemical markers for both impact and eruption. In some layers, glassy spherules from the impact sit near ash beds from the Deccan flows, a sign that Earth was hit by two different kinds of stress in a short span. Putting those signals together helps explain why the end Cretaceous climate swung hard and why ecosystems collapsed at different speeds in different regions. Megascale eruptions run for long times compared with the disasters we train for. Eruptive pulses can last decades. The full episode can span hundreds of thousands of years. Each pulse releases carbon and sulfur gases. Each flow spreads new rock. Each ash layer adds to the load in the stratosphere. These loads change sunlight, rainfall, and ocean chemistry. Seawater records show shifts in carbon isotopes and traces of metals that spike when oxygen falls. On land, soils thin, river systems reroute, and plant communities reorganize. The numbers sit far outside daily experience. A single flow can bury areas the size of states. Total volumes reach into the millions of cubic kilometers. To hold that scale in mind, think of a lava field that would stretch from coast to coast and stack higher than a city skyline, repeated many times over deep time. Earthquakes are the faster face of internal energy. Most people know famous fault lines: San Andreas, the Japan Trench, the Anatolian Fault. But major earthquakes can start chains of failure that spread well beyond the shaking. The Tohoku event in March 2011 ruptured a long patch of subduction zone off northeastern Japan. The seafloor jumped, the ocean heaved, the tsunami rose and ran inland. Backup generators flooded at a nuclear plant, and cooling systems failed. Meltdowns followed, and recovery work lasted for years. At the same time, ports closed, factories halted, and supply chains paused far beyond Japan. One shock became many. This is the pattern planners watch for. Combinations of power loss, contaminated water, blocked roads, and data outages that magnify damage, designs that isolate failures, valves that shut at high shaking, sea walls paired with evacuation routes, backup power placed on high ground reduce the cascade risk. The central United States holds a different example. In 1811, 1812, the New Madrid sequence in the Mississippi Valley produced several large earthquakes over months. People felt them across most of the eastern half of North America. In places, the ground rose and fell. Sand blows erupted. Parts of the river seemed to reverse for a time. As waves passed, the region was thinly settled then. Today, the same zone carries bridges, pipelines, fiber routes, and major rail and barge traffic. A repeat would cut across transport and manufacturing networks at once. Cascades would include fuel supply, grain movement, and power flows between regions. Maps of expected shaking and soil conditions guide retrofits and new designs, but older structures remain at risk. Early warning systems that broadcast seconds of notice are now being built out, so trains can slow, valves can shut, and surgeons can pause before the strong waves arrive. Impact history adds perspective without reducing urgency. Chicxulub, the crater linked to the end of most dinosaur species, was large, but not unique across geologic time. The key drivers for global loss were the materials struck and the amount lofted high into the air, where it blocked sunlight. Dinosaurs ruled land ecosystems for more than 160 million years, yet remained subject to rare but powerful shocks. Modern humans have been here for about 300,000 years. Written records cover only a few thousand. Technology has grown fast in a short time and ties distant regions together. That tie is strength and vulnerability at once. Daily life runs on assumptions that nature will not jump too far, too fast. Stable seasons, steady rainfall, smooth logistics, and power on demand make food, medicine, and communication possible. Each layer of modern life depends on others. A large asteroid, a supervolcano, or a severe solar storm could break those dependencies for months to years. The practical frame is not a date on a calendar, but a checklist. What fails first, how systems isolate faults, and how long backups last. Risk is not eliminated. It is managed by spreading load, adding margin, and planning for safe degradation when parts of the system go offline. The human mind resists acting on risks that are abstract, slow, or rare. Our brains are tuned to nearby threats, predators, rivals, sudden noises, and to rewards we can reach. Psychologists use the term availability heuristic for a habit of thought. We judge how likely something is by how easily we recall examples. Plane crashes, crimes, and storms fill the news and our memory, so they feel common. Events with long cycles or few recent examples feel distant. That shortcut makes sense in daily life. It fails with cosmic or geologic risk, where the gap between events is long and the effects are wide. We also slip into normalcy bias, a tendency to expect tomorrow to look like today, because most days do. Recognizing these patterns helps planners design warnings and drills that cut through bias with clear, simple steps. Media habits widen the gap. Breaking stories with pictures and clear villains get airtime. Slow, probabilistic risks do not. A near miss by a house-sized asteroid is not dramatic video. A coronal mass ejection on the far side of the sun is a curve on a plot. A fault loading over decades is a line on a map. Schools often skim the basics of orbits, solar cycles, magnetic fields, and extinction markers. Many students finish without tools to read a hazard map, interpret a space weather alert, or place a mass extinction on a timeline. Curricula that add these basics: short labs with magnets and coils, crater counts on lunar images, simple orbit simulations, rock columns that show ash and fossil changes, build intuition without heavy math. Correcting the knowledge gap does not require advanced theory. A few clear ideas carry most of the weight. Orbits are paths set by gravity. Small pushes early change paths most. Solar activity rises and falls on cycles. Bursts launch particles and fields that can couple to Earth. Earth's magnetic field is a moving shield, powered by flows in the outer core. It drifts and sometimes weakens. Rock layers, ice cores, and fossils store timelines we can read. With those pieces, people can see why a region prepares for ash, why grids harden transformers, why agencies practice messages about bright sky trails and pressure waves. Large igneous provinces remain an active research area because they tie deep interior processes to surface life. Drilling programs pull cores through thick basalt to date flows and count pulses. Gas inclusions trapped in tiny crystals record the mix of carbon and sulfur released at the time. Seawater chemistry, archived in limestones and shales, shows when oceans lost oxygen and when they recovered. Computer models link gas release to ocean circulation and to how quickly oxygen returns. The details matter because future hazards will not match the past exactly. Only the basic physics repeats. Earthquake science follows a similar path. Map faults, measure strain, and sort, likely shaking by soil type and building stock. The most damaging quakes are not always the largest. Shallow ruptures near cities on soft sediment amplify waves and focus damage. Cascades are a central worry. As seen in Tohoku, a single hazard can trip many systems. The fix is layered: seawalls and evacuation routes for waves, backup power, and cooling on high ground, valves that close gas lines at strong shaking, bridge bearings and base isolators that let structures move without breaking. Each element has to be installed, tested, and maintained. The benefit is measured in systems that keep working when others fail. Impact, eruption, and solar storm planning share common tools: catalogs, sensors, thresholds, and drills. Catalogs list what could fail and what is near it. Sensors watch the key signals: moving dots in the sky, sulfur and ground lift at a caldera, magnetic field tilt at the Sun-Earth line. Thresholds tie data to decisions, so warnings become actions. Drills build muscle memory in agencies and in the public. Each cycle finds weak spots: a sensor that fails in heat, a map not updated, a message that confuses instead of guides. Fixing those weak spots becomes the next project. Life's record adds context that is neither comfort nor doom. Mass extinctions mark hard times. Recovery marks what comes next. After losses, surviving species spread into open niches. New lineages appear. Ecosystems rebuild with different players. Adaptation is not quick or painless. It shows that, given time and ranges of temperature and chemistry that stay within broad limits, complex systems can return. The fact that life persisted through impacts, traps, field changes, and long climate swings shows how wide those limits can be. For planning, that history says two things at once. The range of possible shocks is large, and systems designed with margin and redundancy can ride out more of them. Our solar system carries both order and stress. Yet across deep time, it still offered the rare mix that complex life needs: liquid water, long stretches of moderate climate, a steady sun, and a shield of magnetic field and atmosphere that soften much of the radiation from space. On this base, cells combined, bodies diversified, brains grew, and attention turned outward. The atoms in those bodies were made in stars, carbon, oxygen, calcium, iron, fused in hot cores, and spread by stellar winds and by explosions. We are proof that matter shaped by violent processes can learn, compare, and plan. Because the forces are large, small margins matter. The moon steadies Earth's tilt and sets the pace of tides. Jupiter's gravity changes the traffic of comets and asteroids. Earth's field deflects charged particles. The ozone layer filters ultraviolet light. The oceans store and move heat. None of these shields is perfect. Together, they have been good enough. Across mass extinctions and recoveries, life found paths forward. Intelligence and culture are recent arrivals, but they carry tools that read these patterns and turn them into steps we can take. The same physics that paints Saturn's rings also sculpts destructive waves in giant storms. The same magnetic fields that light auroras can drive currents that stress power grids. The rules do not change when we move from beauty to hazard. Ice crystals grow by simple steps into snowflakes. Shock waves travel through air, water, and rock and leave marks we can trace after an impact or an eruption. Once you see the links, the night sky becomes a set of working parts, not a distant scene. A practical response is to build, reach, and backups. Reach means observing farther with more detail and lead time. Backups are second chances when first plans fail. Space telescopes widen our watch for near-Earth objects, including those hiding in glare. Radar and thermal measurements reveal size, spin, and structures so small, pushes can be tuned. Networks watch the sun and the solar wind, so warnings arrive with time to act. On Earth, grids add hardware that blocks geomagnetically induced currents and adopt procedures that shed load before transformers overheat. Air and water systems stock spares that fit many models. Data centers mirror records in multiple regions. Becoming spacefaring fits the same logic. The goal is not to leave Earth behind. It is to spread risk and learn in tough environments. Mars bases push closed-loop water and air, shielding for radiation, and food systems that survive dust and long winters. Rotating habitats test gentle artificial gravity and quiet, steady light and temperature control. Depots near the moon reduce the cost and time of moving mass. Mining small bodies for water and metals turns hazards into resources and supplies propellant close to where it is used. Each trial teaches something that also helps on Earth. A wider web of knowledge improves daily judgment. Knowing how orbits work explains why early detection beats last-minute heroics. Knowing what a coronal mass ejection is explains why an alert swaps a polar flight route or pauses a satellite maneuver. Knowing how ash abrades and clogs explains why airports close and why roofs need brushing before rain. The terms are simple and useful. Orbit, flare, CME, magnetosphere, basalt, aerosol, shockwave, fault, uplift. With those in hand, numbers fall into place, and advice sounds like common sense. The benefits of defense and exploration spill over. Coatings built to survive micrometeoroids make longer-lived windows and solar panels. Power electronics hardened for storms make grids more efficient in quiet weather. Deep space timing and navigation sharpen logistics and finance. Compact life support systems guide hospital air control and help homes ride through smoke events. Autonomous navigation and robotic grippers tuned for rough terrain assist in mines and disaster zones. Tools built for distant places return as sturdy equipment for farms, clinics, and cities. Spreading human presence beyond one world also makes room for archives, seeds, and skills. Off-planet backups can hold languages, art, records, and code. Seed banks and tissue libraries broaden what can regrow after a loss. Training that rotates crews through many roles preserves knowledge that might thin out with time. Small habits matter. Repair guides that fit in pockets, spare parts that serve many systems, labels and logs that are always up to date. The point is, resilience that scales from a workshop to a city to a fleet. None of this erases risk, it rebalances it. The aim is to keep shocks from becoming breaks, and breaks from becoming ends. Practical work respects limits and buys time. Time lets repairs finish, fields recover, and orbits shift by millimeters per second. Time carries a warning across an ocean before a wave. Time turns a bright dot found in twilight into a future miss, measured in minutes. Concrete projects make these ideas visible. Wide field surveys in both hemispheres scan the sky every few nights. Software stitches dots into tracks and flags risks. A space-based infrared surveyor finds dark, warm objects that ground telescopes miss. Hera will map Dimorphos to tie theory to hardware, and follow-on missions will test rendezvous and gentle towing. At the Sun-Earth L1 point, monitors sample the solar wind. At L5, imagers view eruptions from the side to constrain timing and geometry. Grids link space weather alerts to clear thresholds for action. Satellite operators map warnings to safe modes. Aviation shifts routes when radio fades or dose rises. Volcano networks align gas, ground, and quakes to alert levels linked to ready steps. Education and guidance matter. Simple labs let students feel orbits with a weight on a string, make current with a coil and a magnet, and form craters in a pan of sand. Community drills treat ash like heavy snow, brush roofs before rain, protect air intakes, keep water sealed. Bright daytime fireballs call for short, direct messages. Step away from windows, move indoors, wait for the pressure wave. Clear, repeated practice makes rare steps familiar. Science keeps adding detail that makes action easier. Isotopes in seafloor cores date floods of lava and spikes of ash. Tree rings register summers dimmed by aerosols. Ice holds the memory of solar storms in nitrate spikes and traces of iron from nearby supernovae. Laser ranging shows the moon's slow retreat. Magnetometers show the field's drift. Spacecraft at the edge of the heliosphere count the shift from solar to galactic particles. Each number fits into a model. Each model ties to a decision. Ring systems, auroras, and snowflakes remain good teachers because they are easy to picture, yet rich enough to map to other domains. Rings appear where countless bits of ice and rock share orbits and trade momentum through gentle collisions. The same math helps with satellite traffic and debris avoidance. Auroras trace particles along magnetic field lines. Their shifting curtains hint at currents that also flow invisibly in long power lines. A snowflake's branches grow as water molecules find calm spots on a crystal. The same growth rules explain frost on cables and ice on aircraft. Reach and backups also mean people and places. Telescopes in the south and north hand off targets as the planet turns. Radar dishes and spectrographs on different continents trade nights to follow, spin changes, and outgassing jets. At sea, research ships tow magnetometers and collect cores. On land, observatories and schools host small sensors that feed open databases. Small labs copy key samples and store them cold in multiple regions. Redundant ground stations keep links alive when weather closes in. Storm hardening overlaps with basic safety. Lines are segmented so faults isolate quickly. Transformers include sensors that watch internal heat. Control rooms rehearse playbooks for high current events. Hospitals keep generators and fuel away from flood zones and test them under load. Water plants stock filters and chemicals that handle ash and silt. Airports keep fine filters for jet intakes during dust and ash periods. These details are not glamorous. They turn a day of risk into a long shift rather than a lasting outage. Space habitats extend the same logic. Rotation provides gentle gravity. Water helps block radiation. Crops anchor air and water recycling. Passive thermal designs hold temperature steady without constant power. Tools are chosen for repairability. Fasteners with standard sizes. Panels that open without special rigs. Parts that swap between systems. Software runs in triplicate with voting logic so a single fault cannot steer a vehicle off course. Crew routines balance work, exercise, rest, and quiet time so small problems do not snowball. Risk communication improves when language is plain. A CME with southward field is expected in 12 hours. Reduce load by 10%. Delay non-essential maintenance is clearer than alarm or jargon. Ash fall possible. Brush roofs. Protect intakes. Avoid driving unless needed. Focuses choices. Short messages cut through availability bias and give people actions. Afterward, reports show what forecasts got right, what failed, and what to change. Trust grows when the loop is visible. The archive work is quiet, but deep. Off-planet storage uses cold, stable conditions to keep DNA, seeds, images, and code safe. On Earth, mirrored collections sit far apart. Polar libraries, mountain vaults, and servers in many countries. Catalogs use open formats so future tools can read them. The goal is continuity. If a region falls silent after fire, flood, or ash, the records and tools to rebuild remain elsewhere. None of this cancels the wonder that drew us to look up. It steadies it. A person on a balcony can watch Venus slide down the twilight and, with a little context, see not just a bright point but a world with thick air and slow spin. Someone on a dark road can see the Milky Way and know that our system orbits its center and bobs through its plane, and that both facts have quiet effects here on winds, water, and life. Knowledge does not dim the view. It adds a layer of use. Even small steps count. A local school that installs a magnetometer adds a pixel to the global space weather map. A city utility that stocks spare transformers shortens restoration after a storm. A farm that keeps seed diversity rides out a bad season and helps neighbors. A family that keeps water, lights, and a radio turns a blackout into an inconvenience rather than an emergency. Layer by layer, the system becomes less brittle. Step outside on a clear night and watch for the quiet markers. The moon's horns tilt as it sets. That angle shifts with the season. Orion tips as the hours pass. Its shoulder star, Betelgeuse, hints at stellar lives and endings. High overhead, satellites trace faint lines. Some pass into Earth's shadow and wink out. These sites fold into one story. Patterns that repeat, systems that sometimes surge, and tools that keep pace. The view narrows, the air cools, and the city's hum softens. Above, the planets keep their slow paths. Below, careful systems idle steady, simple, and ready for whatever the sky decides to send next.